So let's take a look. Let's take
It's
a look
audible now.
on some background information.
Okay, thank you. Thank you.
Content delivery network. Content delivery network is a geographically distributed network of cache servers. These cache servers temporarily store frequently accessed cache objects. So, with before content delivery network, okay, without the deployment of a content delivery network, when a distant user wants to access the content from a content provider, YouTube, for example, the user will first have to send their request to the content provider, and then the content provider return with the requested object. Where the requested object or a requested web object can be a video or practically anything that you can see on your browser, which are text, images, video, or sound clips. Since the content provider and the end users can be very distant apart geographically, the turnaround time can be substantial. So, in order to shorten the turnaround time or latency, many content providers deploy content delivery networks. With the content delivery network, when an end user requests an object, rather than sending the request directly to the content provider, the end user first sent the request to a nearby cache server on the content delivery network. If the object is in the nearby cache server, the object is returned to the end user. Since the cache server is nearby, the turnaround time is much shorter than when the end user had to request the object from a distant content provider. In that case, we said that the request for that web object results a hit. We said that this is a hit because the request object is in a nearby cache server. In contrast, if the requested web object is not in a nearby cache server, the cache server forwards the request to the content provider, and the content provider returns the object back to the content delivery network. Back to the cache server, and the cache server forwards the object to the end user. In this case, we have a mess because the requested object is not originally, because the web request was not serviced by the nearby cache server. Now, that cache server has a decision to make. It may cache the object when it arrives, or it may not. So, ideally, we want as many object requests to be surfaced by cache server on the content delivery network as much as possible. The performance metric to measure the effectiveness of a cache server is object hit ratio. If the object hit ratio is 70%, it means that for every 100 received object requests, 70 of them can be serviced by the cache server. There are a few factors that decide the effectiveness or the performance of a cache server. First, request behavior. If request object are rarely being requested, even object is rarely being requested. So what it means is that if an object is once it is being requested, it is not going to be requested again until a long time. Then in that case, caching those objects may not be a good use of cache space. So if we, in the object requests that arrive at cache server, if many of those objects are rarely being accessed again, then in that case, the performance of the cache server may suffer. Thus, another factor is the object size. Due to the limited space of a cache server, the bigger the objects are, the fewer objects we can keep in the cache server, and then in that case, again, the performance suffers. Another major performance factor is the cache algorithm. To decide if to cache a received object, the cache server consults a caching algorithm to decide if to cache the object or not. There are many cache algorithms for content delivery networks. Among them, LFO, Learning-FromOPT, is one of the state-of-the-art AI-based caching algorithms. For the rest of this presentation, we will give an overview of the LFO caching algorithm and a problem about this algorithm that we tackled in our work, and our proposed solution, and our evaluation setup and result. At the end, we're going to conclude this presentation. LFO is an iterative algorithm. It operates based on fixed length time windows. The length of each window is predefined in terms of the number of incoming requests. And so during a time window, as object requests are coming in, LFO collects the request features in terms of the reuse distance of the requested objects, as well as the sizes of those objects. At the end of the window, given the information of all the requests that have arrived during the window, LFO makes the optimal decision to decide if time can go back, what would the best decision that I would have made. And with the the request features and the best decision that LFO could have made. LFO feed these two pieces of information into a library by the name of LGBM, which was developed by Microsoft. This library produces a model. That model basically it contains the mapping between request features and the optimal caching decision that LFO should make in the next window. During the next window, as each request comes in, LFO extracts the feature of that request in terms of the size of the requested object as well as the reuse distance of that object ever since the beginning of the current window. These two pieces of information is fed into the model that was created at the end of the previous window. The model produces a probability of the likeliness. It produces the probability that the object will be requested again. The higher the probability is, the more likely that the request is going to be requested in the near future. So, if the probability is bigger or is at least 0.5, LFO caches the object. Otherwise, it does not cache the object. Please note that unlike conventional caching algorithm, when an object that is currently cached is being accessed, if the model decides that the likeliness or the probability that the object is going to be accessed again is below 0.5, LFO may actually evade that object. So what it means is that an object may be evicted on a hit. This is one of the major differences between LFO and conventional caching algorithms. So, how does LFO deduces the optimal caching decisions? This is how. At the end of a window, LFO looks back all the way to the beginning of the window and then examine requests one by one. These numbers are the object ID of the requested object. 4. Since it is going to be accessed again, then we want to cache it. 2. It will be accessed again. We want to cache it. 3. Since it will be accessed again, we will want to cache it in the optimal decision. Now, 3. It is being accessed a second time, and since it is not going to be accessed, again before the end of the window, we are not going to cache it. For 2, since it is the very last time it was being accessed, and it is not going to be accessed again before the end of this window, we're not going to cache it. So are 1 and 4. However, LFO makes the optimal decision here at the end of the window without knowing what comes next in the future. It doesn't know that 4, 1, and 2 are going to be immediately accessed at the very beginning of the next window. So, therefore, these three decisions, we call them false positive. False negative. The reason is because, let's say LFO knows about what it's going to hold in the future. It would have cached these three objects. They are going to be accessed really, really soon. So LFO better cache it. But now, since it doesn't know about the future, and these objects are being accessed for their last times in the window, and then the best decision that LFO can make is to not to cache them. Remember, cache space is limited. So unless LFO is sure that an object is going to be accessed in the future, it should not cache those objects. And other criteria that LFO uses is the object size. Let's say if I have two objects that are to be accessed and two requests, okay, and two requests of time, both objects are going to be accessed really soon. But one object is small, one object is big. When the cache size is very limited, when the available cache size is very little, LFO is going to prioritize the small object because it is going to produce a hit with a smaller cache overhead. So both the both the object size as well as if an object is going to be accessed again are factors for determining the optimal decision. And similarly, another factor is the reuse distance. If I have two objects, they are of the same size, and both of them are going to be accessed again only once before the end of the window. In that case, and then one of them is going to be accessed in 4 requests. Another one is going to be accessed again in 40 requests. In that case, LFO prioritizes the one that is going to be accessed in 4 requests, but not the one that is going to be accessed in 40 requests. The reason is because the former one produces a hit by staying in the cache for a shorter amount of time. Okay, so this is how the optimal decisions are produced. Okay, false negative. Now, we saw from the previous slide, we saw that 2, 1, and 4 are false positive because even though they are at the end of the window, we see that they are not going to be accessed again. It is reasonable to not cache them. However, in the ideal case, what I mean by ideal is that we know what the future holds. In that case, we would have cached these 3 since they are going to be accessed really soon. In that case, these 3 negatives are false negatives. Now, it is generally true that request characteristics doesn't matter whether they are requests to your content delivery network or requests to your I/O devices. Those requests tend to have certain patterns in terms of reuse distance, the object size. Okay, these characteristics or the behavior of these requests tend to change. They don't always stay the same. And for this kind of fixed windows-based algorithm, The smaller the windows are, the more frequently the algorithm adjusts itself to adapt to the changes in request behaviors. Now, however, our observation shows that as the window size decreases, the probability of false negative actually increases. Here's an example. Let's assume that we reduce the window size from 8 to 4. In that case, 4, we're still going to catch it. 2, 3, and 4, we are not going to catch them. Because by the end of the window, when we look back all the way to the beginning of the window, I know that 2 is not going to be accessed again, 3 are not going to be accessed again, 4 are not going to be accessed again. But when we compare with the ideal case, 2, 3, and 4 are going to be accessed again in the future. So therefore, these 3 are false negative. So by reducing the window size by half, we double the number of false positive. The number of false negatives. So what is the solution? The solution is that we are when we deduce the optimal decisions, we give objects that are being requested for the very last time in a window a second chance. For example, for 2, 1, and 4, before marking them as not to cache, we think again. Are we sure that it is not likely that it is going to be accessed again? The way we answer this question is that is to consult the model that we have been using ever since the beginning of the window. We ask the model again, hey, is this how likely these objects are going to be accessed again? If the model thinks that, hey, it is really, really likely that 2 is going to be accessed again very soon, then in that case, we would mark it as true. We do the same thing to 1 and 4. So, in that case, we're giving a second chance to request an object for the very last time during a window. Since it is a second chance, it is reasonable to set the bar higher. Unless it is really likely that the object is going to be accessed again, we would not grant this second chance. So we call the new bar likelihood threshold. During a window, when the model predicts that an object is at least 50% likely to be accessed in the future, we would catch the object. Now, the likelihood threshold is above 50%. We are going to demonstrate multiple choices of the likelihood threshold when we talk about our evaluation results. This is our evaluation setup. We set up LFO. We implement this algorithm with the name LFO2. We implement it on a simulator by the name of WebCache Sim2. The evaluation workload is called CDN1, which is captured from a production environment. The cache size is set to 256 GB. We want to measure. You use the same metric, which is commonly used by the research community, object hit ratio. We explain what it is when we talk about the background, and then we measure the percentage of false negatives. Now, since we're giving them a second chance, there is a probability that there may be some requests that we really should not catch them, but then we end up catching them. So those, we call them false positive. We're going to measure the probability, the percentage. Now, and then we want to know the overhead of LFO given different likelihood threshold. We are going to evaluate the overhead in terms of cache occupancy. Here's the result. This is the result of LFO given different window sizes. And then, as what we mentioned before, the smaller the window size is, the higher, the more false negative we have. Because of higher false negative value, we have worse performance. And because of the false negative, the model is more likely to reject objects from being emitted. Since fewer objects are being emitted, the cache occupancy is lower. Now, we evaluate LFO2 with a small window size of 2. The reason we pick a small window size is because, again, the smaller the window size is, the more adaptive the algorithm is to changes in request behavior. So even though it is harder to achieve good object hit ratio using small window size, we still pick small window sizes. We evaluate different candidates of likelihood threshold. The bigger the likelihood threshold is, the more picky LFO2 is when granting the second chance. As what we see, as we increase the likelihood threshold, the object hit ratio decrease slightly, all the way from 0.5 to 0.8. Now, as what we see is that while we're using a small window size, even though we are using a small window size, our object hit ratio surpass the object hit ratio even when we were using window size of 8 million in LFO. The performance of LFO2 surpasses the performance of LFO by almost 10%. So how could that be possible? This is made possible because LFO2 significantly decreases the number of false negatives when deducing optimal decisions, from 21% all the way to negligible. And as what we see here, when we use 2 million as the window size of LFO, nearly 1/3 of their predictions of false negatives. Okay, as mentioned, since we are giving a second chance, LFO2 may mistakenly give second chance to objects that do not deserve a second chance. Those objects are not going to be accessed anytime soon. Yet, LFO2 mistakenly give them a second chance and suggest to emit them. But we find that LFO2 is able to cap the percentage of false negative by 4%. And so, Is there any overhead? Yes, because it is more likely, because their optimal decision, yeah, I mean, admit object more likely. So, which means that the model that is produced based on the optimal decision produced by LFO2 are more likely to admit requested object. Therefore, more objects are to be admitted into the cache. Now, rather than saying that it is an overhead, we would argue that it is just because LFO2 make better uses of the cache space. The cache space is an investment. We bought it already. We want to make good use of it to contribute to the object hit ratio. So, therefore, the increase in the cache space is justifiable. Conclusion: LFO suffered from false negative. LFO2 correct the problem by granting second chances to objects that are being requested for their last time during a window. We are able to achieve high object hit ratio even with small window sizes. Our future work is to continue investigating how to apply AI technologies for CDN caching. And this is the end of our presentation. Thank you for listening.